All right, let's talk about something huge, and I mean literally huge, big data. Today we're going to break down some of the incredibly smart ways we can handle data that's just too big, too fast, or too weird for our usual tools.
So let's just jump right in with a scenario that some of you have probably lived through. Your trusty relational database, the one that's been the backbone of everything, it's full. It just can't keep up anymore. And this isn't just about getting a bigger hard drive. This is a totally different kind of problem.
And to give you a sense of the scale we're talking about, look at this number, 15 petabytes. That's 15 million gigabytes. That is how much data the Large Hadron Collider spits out every single year. We are talking about just an absolutely astronomical amount of information. Now, this data explosion is usually described by what we call the 4 V's. You've got volume, which is that sheer scale we just mentioned. Then there's velocity, the insane speed the data comes at you. Variety means it's not just in nice, neat tables anymore. It's everything: text, images, videos, sensor data. And finally, veracity, which reminds us that all this data can be messy and uncertain. Put them all together, and our old ways of doing things just kind of break.
Let's just zoom in on that velocity problem for a second. In some cases, like in high-frequency trading or scientific experiments, data is streaming in so fast that you literally cannot write it all to a disk. The information is showing up faster than your storage can handle it. That's a whole new ballgame.
So that brings us to the million-dollar question, right? If you can't even save all the data, how on earth are you supposed to analyze it? You can't just give up. You need a new toolkit, a whole new set of strategies built for this fire hose of information. And that leads us to our very first strategy, smart sampling. The idea itself is pretty simple, something we all get. You don't need to drink the entire ocean to know that it's salty. You just take a small sample and you analyze that instead. But, here's the catch. The big one. Normally, when you take a sample, you know how big the whole thing is. But with a data stream, it might as well be infinite. You have no idea when it's going to stop or how much data is coming. So how do you pick a random sample from everything when you don't even know what everything is? Well, the answer is this really elegant algorithm called reservoir sampling. It is just a beautiful piece of computer science that solves this exact problem: how to keep a truly random sample of a fixed size from a stream of totally unknown length.
So how does this magic work? It's actually pretty cool. First, you just create your reservoir and fill it up with the first K items that come along. That's the easy part. Now, for every single new item that arrives after that, let's say it's the nth item, you make a choice. You generate a random number j between 0 and n, and if that number j happens to be less than your reservoir size k, you kick out the item at position j and replace it with the new one. If not, you just let the new item fly on by.
Now, the math behind this is it's perfect. This super simple process guarantees that at any given moment, the items in your reservoir represent true, fair, random sample of every single thing the stream has shown you so far. It's brilliant. Okay, on to our second strategy. This one involves a fascinating trade-off. What if I told you you could get an answer that was almost always right, in exchange for being mind-blowingly fast and efficient? Well, welcome to the world of probabilistic filters.
Let's set up the problem. Imagine you're seeing billions of items stream past, maybe user IDs or URLs, and you just need to know for each one, have I seen this specific one before? Storing every single item you've ever seen is just impossible. You'd run out of memory instantly. So, how do you check?
The solution is a fantastic data structure called a Bloom filter. It's built to do one thing and one thing only. Answer that question, is this in the set, using a ridiculously tiny amount of memory, with the small catch that it might be wrong once in a while.
So how does it work? Okay, picture a really long row of light switches, and they're all turned off. When a new item comes in, you run its name through a few different hash functions. Think of these as machines that each point to one of the light switches. You go to those switches and you flip them on. That's it. Now to check if you've seen an item before, you do the same thing. Run it through the hashers and go look at the switches they point to.
And here is the genius part. If you go to check the switches for an item and even one of them is off, you know with 100% certainty that you have never seen that item before. A false negative is impossible. But if all the switches are on, it probably means you've seen it. There's a small chance that those switches were flipped on by other items. That's a false positive. So it might say yes when the answer is no, but it will never say no when the answer is yes.
So why does this matter? Because for tons of applications, like a web browser checking a URL against a list of millions of malicious sites, a small chance of a false alarm is totally fine.
It lets you do this check on a massive scale using a tiny, tiny fraction of the memory. It's a game changer.
All right, our third and final strategy is all about using what are called clever sketches. This is another way to get the big picture by creating a tiny summary of a huge stream of data.
A Bloom filter is great at telling you if you've seen something, but it can't answer a different, really important question. How many unique items have I seen in total? Seeing apple, then orange, then apple again. A Bloom filter can tell you it's seen both, but it can't tell you that there were only two distinct fruits.
And that's exactly where a numeric sketch comes into play. It's another one of these small, memory-friendly data structures, but it's designed to answer these big-picture questions about the whole stream, giving you a really good approximation instead of a perfect count.
One of the most famous examples, and it has a great name, is the HyperLogLog algorithm. It uses some mind-bending probability and hashing to estimate the number of unique items in a stream of billions, with usually just a tiny error rate, all while using just a few kilobytes of memory. It's practically magic.
And the power of this is huge. This is what allows a service like Google to estimate how many unique search queries were made today, or a big website to count its distinct visitors, without needing a building full of computers just to store the list. It makes these enormous calculations actually possible.
So, as we wrap this up, what's the common thread here? All these strategies, the sampling, the filters, the sketches, they all represent a really fundamental shift in how we think about data. It's about moving away from demanding perfect, precise answers for everything, and instead embracing the power of good enough, probabilistic answers.
And that really is the key takeaway. When you're dealing with data on this kind of scale, an approximate answer that you can get right now is often way more valuable than a perfect answer that you'd have to wait years for. It's about being smart, being efficient, and getting an answer that's good enough to act on. And that's our look at tackling big data streams. Hey, if you found this useful, do me a favor and hit that like button, share it with someone who might be interested, and subscribe for more deep dives into complex topics. Thanks so much for tuning in.